Okay, we are started stream. I see it on my endpad. Let's go to the stream manager. So yeah, I think we are good. We can start. And yeah, still reading Rust book. We finally get to some exciting point. This is understanding ownership. So ownership is Rust's most unique feature. So you see, most unique feature of the Rust, and we will start learning it today. So this is very exciting. So most unique feature, and has been implication for the rest of the language. It enables Rust to make memory safety, guarantees without needing a garbage collector. So it's important to understand how ownership works. In this chapter, we will talk about ownership as well as several related features, borrowing, slices, and how Rust lays data out in memory. Okay, this is really cool. The stack and heap. Yeah, this is actually, I would like to see what we will learn about it today. So what is ownership? Ownership is a set of rules that govern how a Rust program manages memory. All programs have to manage the way they use a computer's memory while running. Some languages have garbage collection that regularly looks for no longer used memory as the program runs. In other languages, the programmer must explicitly allocate and free the memory. Rust uses a third approach. Memory is managed through a system of ownership with a set of rules that the compiler checks. If any of the rules are violated, the program won't compile. None of the features of ownership will slow down your program while it's running. So yeah, I like being in this situation, like when I start in the probably 2010, 2011, started with Objective-C, and those days you need to explicitly allocate memory. But yeah, then there was new version of the Objective-C where garbage collection was introduced. So I saw both concepts in one language, and Rust has its unique way to handle this problem. As it say, it's ownership, and as I understand from this first introduction, it's like force you to write code the way where you don't need to either garbage collector nor like explicitly free the memory. So let's continue. Because ownership is a new concept for many programmers, it does take some time to get used to. The good news is that the more experienced you become with Rust and the rules of the ownership system, the easier you'll find it to naturally develop code that is safe and efficient. Keep at it. Okay. Safe and efficient. This is what we want. When you understand ownership, you have a solid foundation for understanding the features that make Rust unique. In this chapter, you learn ownership by working through some examples that focus on very common data structure, strings. Alright, so this is some notation area, the stack and heap. Many programming languages don't require you think about the stack and the heap very often. But in systems programming languages like Rust, whether a value is on the stack or the heap affects how the language behaves and why you have to make certain decisions. Part of the ownership will be described in relation to the stack and the heap later in this chapter. So here is a brief explanation in preparation. Both stack and the heap are parts of memory available to your code to use at runtime, but they are structured in different ways. The stack stores values in the order it gets them and removes the value in the opposite order. Okay, maybe I don't know, maybe I should use some drawing tool to visualize things. Drawing online. AutoDraw, Sketch.io, I don't know, let's start drawing. So the stack, let's imagine it's something like this, and we have some coins. So we add them in the order. There is 1, then we can add 2, and then 3. When we want to get something from it, we start in with 3, then we go into 2, and then last will be 1. At least as I understand what I just read. So the stack stores in order it gets them and remove the value in the opposite order. This referred to as last in, first out. It's back in the days, yeah, abbreviation was LIFO. Like I think it's still LIFO, but I never, I didn't hear it recently because, yeah, I don't really work with such things like low level. Think of stack of plates. So yeah, basically you put plate, then on top your plate new one, new one, new one, and when you want to get to the one it's underneath, you should take all from the top. When you add more plates, you put them on top of the pile, and when you need a plate, you take one off the top. Adding or removing plates from the middle or bottom wouldn't work as well. Adding data is called pushing onto the stack. So when we add data, we call, yeah, so we do pushing onto the stack. And removing data is called popping of the stack. So push and pop. Okay. All data stored on the stack must have a known fixed size. So yeah, if we play something, we should know its characteristics. Data with an unknown size at compile time or a size that might change must be stored on the heap instead. So there is the second concept is heap, which use for things that changing. The heap is less organized. When you put data on the heap, you request a certain amount of space. Okay, so start over. So we have heap and we ask give us, I don't know, 5 bytes. Certain amount of space. The memory allocated found an empty spot in the heap that is big enough, marks it as being in use, and return a pointer, which is the address of allocation. So yeah, let's back to our drawing. So if we have many allocated and we want something like big, we cannot place it here, we need to take it somewhere from the here because this place is not fit. So allocator need to find the place. So it's I think this is why it's less efficient compared to stack. And then it back as pointer. So and it's something like the address of the memory, I don't know, some number. Okay, and return a pointer which the address of the location. This process is called allocating on the heap and is sometimes abbreviated as just allocating. Pushing values onto the stack is not considered allocating. Okay, because the pointer to the heap is a known fixed size, you can store the pointer on the stack, but when you want to the actual data, you must follow the pointer. So yeah, we now when we get this pointer, we can place it in our stack. Let's name it P1. Yeah, because we know the size of the address in memory. Think of being seated at a restaurant. When you enter, you state the number of people in your group, and the host finds an empty table that fits everyone and leads you there. If someone in your group comes late, they can ask where you've been seated to find you. So like we need a table for 1, 2, 3, 4, maybe 5, but we can change it. We can use 4 and then 5 come later, but he can find you getting the pointer which directs to this. Not sure if the pointer should be always in stack, but might be. Pushing to the stack is faster than allocating on the heap because the allocator never has to search for a place to store new data. The location is always at the top of the stack. Comparatively, allocating space on the heap requires more work because the allocator must first find a big enough space to hold the data and then perform bookkeeping to prepare for the next allocation. So yeah, we kind of mention it. Accessing data in the heap is slower than accessing data on the stack because you have to follow a pointer to get there. Contemporary processors are contemporary is a synonym of modern. Processors are faster if they jump around less in memory. Counting the analogy, consider a server at a restaurant taking order from many tables. It's most efficient to get all the orders at one table before moving on to the next table, taking an order from the table A, then an order from table B, then one from A again, and then one from B again would be much slower process. But the same token, a processor can do its job better if it's work on data that's close to the other data, as it is on stack, rather than further away, as it can be on the heap. So yeah, basically we have two models. One is stack. We know the characteristics of each piece of data we place there, like we know the size and we have special order, so everything works efficient. And then we have heap where we can allocate, like find the place for different sizes and use it like something what will be dynamically changed during the program is working. So it's less structured, so it less efficient. So this is, I think, main take so far. When a code calls a function, the values passed into the function, including potentially pointers to data on the heap, and the function local variables get pushed onto the stack. Yeah, let me read this again. When a code calls a function, the values passed into the function, so yeah, it's when the function is over, those values get popped off the stack. So yeah, if you have ever debug any code, you heard this stack trace or you see this stack of functions, and you can move over this stack for debugging purpose to see what on each level is stored, so you can easily visualize what it is like. Yeah, each function invocation placed like if you're trying to image it again, so here's our stack. I think even yeah, let's go to main RC. So we have main function, so it placed to the bottom of the stack. Then we have another function, so another function place here, but once it finished, it will pop from the stack. So we push it to the stack, then it pop, but main is still there because it's not finished, and we will invoke next try expression function. Sorry, yeah. Try, then it go there, basically on a place where another function was. Once it's finished, popped from the stack, and then the main is finished and also popped from the stack. Okay. Keeping track of what parts of code are using what data on the heap, minimizing the amount of duplicate data on the heap. Keeping track of what parts of code are in. And cleaning up unused data on the heap, so you don't run out of the space, are all problems that ownership addresses. So ownership is keeping track of what parts of code are using what data on the heap, minimizing the amount of duplicated data, and cleaning up unused data on the heap. So okay, once you understand ownership, you won't need to think about the stack and the heap very often, but knowing that the main purpose of ownership is to manage heap data can help explain why it works the way it does. So yeah, I think this stack and heap kind of clear right now, so we can continue with ownership rules. Okay, first let's take a look at the ownership rules. Keep those rules in mind as we work through the example that illustrate them. Each value in Rust has an owner. Okay, each value has an owner. Okay, there can only be one owner at a time. When the owner goes out of scope, the value will be dropped. So it's a drawing day. So there is an apple. It's a value. And a value should have an owner. And it's not possible to have two owners or more than one owner. And once the owner is not there, we drop the information about value in the heap, I guess. I think quite clear so far. So variable scope. Now we are past basic Rust syntax. We won't include all the fn main code in examples. So if you are following along, make sure to put the following examples inside the main function manually. As a result, our examples will be a bit more concise, letting us focus on the actual details rather than boilerplate code. Sure, not a problem. As a first example of ownership, we'll look at the scope of some variables. A scope is the range within a program for which an item is valid. Take the following variable. Okay. First of all, let's create new project. Cargo ownership. In the main Rust, let s hello string. The variable s refers to a string literal where the value of the string is hard-coded into the text of our program. The variable is valid from the point at which it declared until the end of the current scope. Listing for 1 shows a program with comments annotating where the variable would be valid. S is not valid here, it's not yet declared. S is valid from this point, and then we can have the code which operate with S here, and this scope is now over and S is no longer valid. Okay. Yeah, I just think we should probably update stream description ownership. I think exciting topic. So basically, if you look, yeah, until the curly brackets closed of main function, our s variable will be valid, or if we have some inside block and create w yeah, something like this. W is not valid here. Exactly. In other words, there are two important points in time here. When s comes into scope, it is valid, it remains valid until it goes out of scope. At this point, the relationship between scopes and when variables are valid is similar to that in other programming languages. Now we'll build on top of this understanding by introducing string type. Alright. So yeah, this is common situation for at least languages I knew. So the string type. To illustrate the rules of ownership, we need a data type that is more complex than those we covered in the data types of section of chapter 3. The types covered previously are of a known size, can be stored on the stack and pop off the stack when their scope is over, and can be quickly and trivially copied to make a new independent instance if another part of code needs to use the same value in a different scope. But we want to look at data that is stored on the heap and explore how Rust knows when to clean up that data. And the string type is a great example. We'll concentrate on the part of strings that relate to ownership. Those aspects also apply to other complex data types, whether they are provided by the standard library to create by you. We'll discuss string in more depth in chapter 8. Yeah, string is big topic for any language. You do a lot of things with string while you create programs. We've already seen string literals, where a string value is hard-coded into our program. Strings literals are convenient. Yeah. But they aren't suitable for every situation in which we may want to use text. For sure. One reason is they immutable. Yeah, for sure we want to mutate strings at some point. Another is that not every string value can be known when we write our code. For example, what if we want to take user input and store it? For those situations, Rust have a second string type string from the capital letter S. This type manages data allocated on the heap and as much is able to store an amount of text that is unknown to us at compile time. You can create a string from a string literal using the from function like so. And we're gonna do it. So let us string from double colon the double colon operator allows us to namespace this particular from function under the string type rather than using some sort of name like string from. We'll discuss the syntax more in the method syntax section of chapter 5, which is next chapter. So kind of soon we will learn about it. And when we talk about namespacing with modules in passes for referring on an item in the module 3 and chapter 7, need to wait a bit for it because a lot of things to learn before. This kind of string can be mutated. So finally we can mutate our string. Let's do it as push str just same and of course we have an error here because Rust says cannot borrow as mutable, as it is not declared as mutable, cannot borrow as mutable. So we need to add mut here, and of course we want to print cargo run hello world. But we need mut for s to be able to change it. So what the difference here? Why can string be mutated but literals cannot? The difference is in the how these two types deal with memory and allocation. Okay, let me do a sip of tea. In the case of a string literal, we know the content at compile time. So the text is hard-coded directly into the final executable. This is why string literal are fast and efficient, but these properties only come from the string literal's immutability. Unfortunately, we can't put a blob of memory into the binary for each piece of text whose size is unknown at compile time, and those size might change while running the program. Okay. This is actually interesting. So I guess when we run the program, it allocate memory for the stacks known amount. No, it's maybe wrong. Let's continue. With the string type, in order to support a mutable, growable piece of text, we need to allocate an amount of memory on the heap unknown at compile time to hold the contents. This means the memory must be requested from the memory allocator at runtime. We need a way of returning this memory to the allocator when we've done with our string. That first part is done by us when we call string from. Its implementation requests the memory it needs. This is pretty much universal in programming languages. However, the second part is different. In languages with garbage collector, the garbage collector GC keeps track of and cleans up memory that isn't being used anymore, and we don't need to think about it. In most languages without a GC, it's our responsibility to identify when memory is no longer being used and to call code to explicitly free it, just as we did to request it. Doing this correctly has historically been a difficult programming problem. If we forget, we'll waste memory. If we do it too early, we'll have an invalid variable. If we do it twice, that's a bug too. We need to pair exactly one allocate with exactly one free. Rust takes a different path. The memory is automatically returned when the variable that owns it goes out of scope. Here is a version of our scope example from listing 4.1 using string instead of a string literal. So after closing curly bracket, the scope is now over and S is no longer valid. Yeah, sounds super logical, actually. There is a nature point at which we can return the memory our string needs to the allocator when S goes out of scope. When a variable goes out of scope, Rust calls a special function for us. This function is called drop. It's a link. Let's take a look. It's docs rustlang.org function drop. Ampersand mat self. Execute the destructor for this type. Okay. So yeah, and it's where the author of string can put the code to return the memory. Rust calls drop automatically at the closing curly bracket. Note, in C++ this pattern of deallocating resources at the end of an item's lifetime is sometimes called resource acquisition is initialization. RAII. The drop function in Rust will be familiar to you if you used this pattern. Yeah, I think I used something like this back in the day, so something like deallocate keyword, but yeah, it was a long time ago. This pattern has a profound impact on the way Rust code is written. It may seem simple right now, but the behavior of code can be unexpected in more complicated situations when we want to have multiple variables use the data we allocated on the heap. Let's explore some of those situations now. Yeah, first I read it, it sounds like super logical, simple, but what they deal with this ownership stuff. Variables and data interacting with move. Multiple variables can interact with same data in different ways in Rust. Let's look at an example using an integer in listing for 2. So we create let x equal 5, then let y equal x. We can probably guess what this is doing. Bind the value 5 to x, then make copy of the value in x and bind it to y. We now have two variables x and y and both equal 5. This is indeed what is happening, because integers are simple values with a known fixed size, and these two 5 values are pushed onto the stack. Now let's look at the string version. Yeah, this is definitely more interesting because the value hello is stored in the heap and we have pointer to the place in heap. And I guess S2 use pointer to this value. This looks very similar, so we might assume that the way it works would be the same. That is, the second line would make a copy of the value S1 and bind it to the S2. But this isn't quite what happens. Take a look at figure 4.1 to see what is happening to string under the covers. A string is made up of 3 parts, shown on the left. A pointer to the memory that holds the content of the string, a length, and capacity. This group of data is stored on the stack. On the right is memory on the heap that hold the content. So this is our S1. So we have a pointer which points us to the place where first letter H stored, and we know the length of kind of size, how many bytes, probably bytes, we need for each, like for whole string. So we need 5, so next 4 byte in memory is also our value. But what is capacity then? Oh, capacity is probably is allocated part. So if we, for example, have capacity 5, but we use only like 2, like here, HE, and this one is unused yet, and we can modify it. I guess this is what it is. The length is how much memory in bytes the contents of the string are currently using. The capacity is total amount of memory in bytes that the string has received from the allocator. The difference between length and capacity matter, but not in this context. So for now it's fine to ignore the capacity. Yeah, this is what I actually thought. When we assign S1 to S2, the string data is copied, meaning we copy the pointer, the length, and the capacity that are on the stack. We do not copy the data on the heap that the pointer refers to. In the other words, the data representation in memory looks like this. So we have same pointer, same length and capacity. The representation does not look like figure 4.3. Which is what memory would look like if Rust instead copied the heap data as well. If Rust did this, the operation S2 equal S1 could be very expensive in terms of runtime performance in the data on the heap were large. So yeah, as we know, allocating is comparably expensive. So if we do it twice, it will be much more slower than just point to the same place in memory. Earlier, we said that when a variable goes out of scope, Rust automatically calls the drop function and cleans up the heap memory for that variable. But figure 4.2 shows both data pointers pointing to the same location. This is a problem. When S1 and S2 go out of scope, they will both try to free the same memory. This is known as a double free error and is one of the memory safety bugs we mentioned previously. Freeing memory twice can lead to memory corruption, which can potentially lead to security vulnerabilities. To ensure memory safety, after the line let S2 equal S1, Rust consider S1 as no longer valid. Therefore, Rust doesn't need to free anything when S1 goes out of scope. Check out what happens when you try to use S1 after S2 is created. It won't work. And for sure, we're going to try it. And we immediately see the error. So S2 borrowed the S1 value. And to be sure, we will run and see the error. Basically same error, value borrowed here after move. If we replace it with S2, it works just fine. Okay. You'll get an error like this because Rust prevents you from using the invalidated reference. So this is the rule. Like we have 3 rules. Each value in Rust has an owner. So have S1 owner of this value, and there can be one owner at a time. So here we have this rule. When we use value of S1, S2 become an owner, and S1 is no longer an owner of this. So trying to use S1 produce an error. Good. I think we go too far. Yeah. If you heard the terms shallow copy and deep copy while working with other languages, the concept of copying the pointer length and capacity without copying the data probably sounds like making a shallow copy. But because Rust also invalidates the first variable instead of being called a shallow copy, it's known as move. In this example, we would say that S1 was moved into S2. So what actually happened is shown here. Just for a second, back to our code, and the where our error. So yeah, value borrowed here after move, borrow of moved value. So yeah, after we introduce this term move, this error makes much more sense to me. So S1 was moved to S2, and after the move it's not valid. Simply grayed out S1 doesn't really clear representation, but yeah, it means it's invalid. So that solves our problem with only S2 valid. When it goes out of scope, it alone will free the memory, and we are done. In addition, there is a design choice that implied by this. Rust will never automatically create deep copy of your data. Therefore, any automatic copying can be assumed to the inexpensive in terms of the runtime performance. So Rust don't do any deep copy automatically, so any automatic copy is not deep, that's why it's inexpensive. Okay, makes sense. Variables in data interacting with clone. So yeah, if I think clone means we actually want to copy S1 to S2. If we do want to deeply copy the heap data of the string, not just the stack data, we can use a common method called clone. We'll discuss method syntax in chapter 5, but because methods are common feature in many programming languages, you've probably seen them before. Here is an example clone method in action. And we immediately trying it. And of course we want to print S2. We actually want to print balls. Okay. Nothing fancy, just two same string printed. This works just fine and explicitly produces the behavior shown in figure 4-3, where heap data does get copied. When you see a call to clone, you know that some arbitrary code is being executed and that code may be expensive. It's a visual indicator that something different is going on. Stack only data copy. Yeah, just recheck the figure 3-4-3. There is another wrinkle we haven't talked about yet. This code using integers, part of which was shown in listing 4.2, works and is valid. But this code seems to contradict what we just learned. We don't have a call to clone, but X is still valid and wasn't moved into Y. This reason is that types such as integer that have a null size at compile time are stored entirely on the stack, so copies of the actual values are quick to make. That means there is no reason we would want to prevent X from being valid after we create the variable Y. In other words, there is no difference between deep and shallow copying here, so calling clone wouldn't do anything different from the usual shallow copying, and we can leave it out. Rust has a special annotation called the copy trait that we can place on types that are stored on the stack. As integers are, we'll talk more about traits in chapter 10. If a type implements the copy trait, variables that use it do not move. but rather trivially copied, making them still valid after the assignment to another variable. Okay. So let me think a bit about it. Okay, so if we want to do some type not move, we should implement some protocol copy, which is not really protocol but some trait we will learn in chapter 10. Okay. Rust won't let us annotate a type with copy if the type or any of its part has implemented the drop trait. If the type needs something special to happen when the value goes out of scope and we add the copy annotation to the type, we'll get a compiler time error. To learn about how to add the copy annotation to your type to implement the trait, see derivable traits in appendix 3. Let's quickly look into it. But yeah, a lot of stuff here. There is something about copy. Okay, I don't see interesting examples here for now. So let's jump back. So what types implement the copy trait? You can check the documentation for the given type to be sure, but as a general rule, any group of simple scalar values can implement copy, and nothing that requires allocation or is some form of resource can implement copy. Here are some of the types that implement copy. All integer types such U32. The boolean type bool with values true and false. All the floating point types such F64. The character type char. Tuples if they only contain types that also implement copy. For example, i32 implements copy, but i32 string does not. Okay. Ownership and functions. The mechanics of passing a value to a function are similar to those when assigning a value to a variable. Passing a variable to a function will move or copy, just as assignment does. Listing for 3 has an example with some annotations showing where variables go into and out of scope. So let's read it. So we create a string as come to into scope, take ownership as values move into the function, and so is no longer valid here. And I want to try it. So if I will try to print the S after the move, I will get an error because S was borrowed of moved wallet. Okay, it was moved here. So if I want to maybe need to sorry, I probably need to return some string. Now we had there because we don't have return value specified. But if we do like this, and if we we can do it like this. And cargo run. Yeah, it works. And with how it was called, in the variables chapters, shadowing, we can do shadowing. So we can, since S no longer will be valid, but we don't want to create the variable with new name, because it kind of starting become a mess, like each. So we can do just like this, and it should work just fine. Now I get this feature. Now it makes more sense. Shadowing. It's quite cool. So yeah, we moved the value, so we would like to move it back. Okay. If we try to use S after the call to the take ownership, Rust would throw a compile time error. These static checks protect us from mistakes. Try adding code to main that uses S and X to see where you can use them and where the ownership rule prevents you from doing so. And yeah, it shouldn't be a problem to use X after. Yeah, because it's in the stack and it implements copy, so there is no deep copy. Return values and scope. Return value can also transfer ownership. Shows an example of the function that returns some value with similar annotation as those in listing for tree. So basically, gives ownership. Yeah, this is what we did. We write it in advance. So here we send S2, it's no longer valid, and we assign it to S3 because we do a return. Only shadow missing here, but yeah. The ownership of a variable follows the same pattern every time. Sorry, I need a drink a bit. The ownership of a variable follows the same pattern every time. Assigning a value to another variable moves it. When a variable that encodes data on the heap goes out of scope, the value will be cleaned up by drop unless the ownership of the data has been moved to another variable. While this works, taking ownership and then returning ownership with every function is a bit tedious. What if you want to let a function use a value but not take ownership? It's quite annoying that anything we pass in also need to be passed back. If you want to use it again, in addition to any data resulting from the body of function that we might want to return as well. Rust does let us return multiple values using a tuple as shown in listing. So we can return both. But this is too much ceremony and a lot of work for a concept that should be common. Luckily for us, Rust has a feature for using a value without transferring ownership called references. Oh yeah, references sound great, and it will be in the next section, but yeah, I think that's big concept to take a look today, so we will back to it in the next stream. Maybe I'll be busy next couple days, so probably on the weekend. So yeah, thanks for watching, see you next time.